Right. Subspace, when we're talking about a subspace, what we're talking about is where the vectors can go. And it's kind of like that last problem. If you have a plane and a point that's off of it, you can't get to that point if you're bound to a plane. So a subspace is a realm of values, non-empty. Okay, that means the vectors have to be in it, such that it's closed under addition and multiplication. In other words, the vectors can get longer, shorter, or they can add or subtract. Okay? We have to prove both of these, actually all three of them. This has one part, this actually has two parts to it, but we have to prove. Well, non-empty is simple. We just put in a 0, no problem. But you also have to show that you can add and you can multiply and you still get in the same space. Ooh, tough. Let's see an example. Okay? And for this one, the subspace is a space in 3 dimensions, that's what our cubed is, that you're going to be able to take this and say those 3 things. The first thing we can do is we can put a 0 in for x and y. So we set x equal to 0 and y equals 0, and you get 0, 0, 0 plus 0 is 0. And because you get the 0 vector, that's still a vector, and it means it's non-empty. It's just a quick way to double check.
What would fail that? What would fail that?
X over y?
Okay. Oh, okay. Oh, also, another question.
Yeah.
Because there's an identity matrix, is there an I matrix, like an imaginary matrix?
Not in R2 or R3 or R4. It might be a complex RI space that I've never studied, but it sounds fascinating. Now, the next thing that we're going to do is we're going to take 2 vectors. We're going to call it U and V. And vector U is going to be x1, and vector V is going to be x2. Can you write this down? This example is going to help a lot. Then, instead of y, we have y1 and y2. Instead of x plus y, we have x1 plus y1. And x2 plus y2. This is the part that we're getting into nitty-gritty here. We have to say it's in W, and when we prove the second part, C is going to have to be an element of the reals. So we're going to say U is this, V is this, in W, because that's W, and C is an element of the reals. We're going to use that in that scalar multiplier. So let's add them together. When we add these, you're going to get x1, y1, x1 plus y1, plus x2, y2, x2 plus y2. When we put them together, you get x1 plus x2, y1 plus y2, and notice you have a group of x1 plus x2 and y1 plus y2. Does this here look similar to that? Is that the same form? It is. Right down to these variables would compare to this one. These to this one. These 2 paired up would give you those 2. So the addition part and the non-empty part, accomplished. Mission accomplished. Now we're going to do the multiplier part. That's the third part of the second part of 2. We're going to take C times U, and when we do that, it should give us the same thing. So C times x1, and you don't need to worry about V. It's just one is one or the other. We're going to use U. Cx1, Cy1, Cx1 plus Cy1. Does this form look like this form? Yeah. So what we're saying then is since it's non-empty and it's closed because the forms are the same for addition and scalar multiplication, W is in the subspace of R3. The W we've defined here. Break what?
How would you not need that requirement?
So what you would start with here is you need to define U. So you would set let U, this is a vector, be equal to x1 minus 3, and Z we're going to call, they used U, didn't they? Excuse me. I'm going to be consistent here. U1 minus 3, this would be U3. And V would be V1 minus 3, V3.
I think you were right the first time. Where you were using x1, z1, x2, z2.
You could.
Oh,
That's what the other example did? Excuse me. Yeah.
Oh, should that be U2 minus 3 then?
No, there's no Y in here. It's just X and Z. Isn't that
But it doesn't really matter.
irritating? Yeah. And then, and we would also add where this is an element of W. These two are elements of W, and C is an element of the reals, which we're going to get to. Oh, wow. I don't want to give it away. That help getting the start? Now, see what U plus V is. And tell me what you see. U1 plus V1, I see that. I get U1 plus V1 minus what? 6. And then I'm going to get U3 plus V3. Tell me about U1 plus V1. Is that kind of a match for X? And is U3 plus V3 a match for Z? Is U1 plus V1 a match for X? Yep. Is negative 6, to go back to blue, is negative 6 a match for negative 3?
How would you formally prove that?
I don't know, but because this would be in a different place, 6 is different. Well, he's not asking is 6 different than 3. How is this being off by 3 different? It moves it into a different y plane. So then what you would say there is, therefore, U plus V is not an element of W, since U1 plus V1 minus 6 is not equal to U1 plus V1 minus 3, which is what it would need to be. And then you would say, therefore, W is not closed under addition. Want some good news? Then we don't have to check multiplication. By the way, what would happen with the multiplication? If you did the C times the U. What do you think would happen to that? It still would probably be okay, wouldn't it? But it would, but because it's not closed here, it's not closed under addition. That's part I want to say. Therefore, W is not a subspace of R cubed. Now, you can do the rest of these problems. I just want to make this last statement. If you're having a hard time picturing this, you know, what they mean by W not fitting in the subspace, it's okay. I'm not sure I totally get it either. Do your best. If you get some visions, let me know. But following through, we just have to have form fits in order to be closed under addition and scalar multiplication.